Everybody, and I would like first of all to thank very much Irene for accepting our invitation to give this plenary colloquium of the Italian Society of Statistical Physics and Complex Systems. It's really a great pleasure, also because we want that our female colleagues participate deeply and importantly in these kind of seminars. And Irene, as all of you know, most of you know, is presently full professor of theoretical physics at the University of Rome, La Sapienza, and she is a renowned expert of complex systems, statistical physics and complex systems. And in particular, she has given outstanding contributions in models of biophysical systems and clocks and collective behavior of living systems and so on. And actually, the title of this seminar, or her plenary colloquium this afternoon, concerns exactly flocking systems, which is a very impressive and imaginative area of research in our field. So please, Irene, it's your time. Thank you very much again.
Thank you, Roberto, for this nice introduction. So let me share my presentation. Okay. Okay, can you see the presentation?
Yes, it is not full screen, but it's okay.
Yes, now I'm going full screen. Okay. Okay, now it should be fine.
Yes.
Okay, so as Roberto mentioned already, with my group, we are interested and we have been studying collective behavior in biological systems, and in particular, for a long time, we have been studying the behavior of flocks of birds and swarms of insects. Now, collective behavior in biological systems occurs at many scales, and here in the top row, you can see a few examples. All these examples are from experiments that we do in our group. So we recently also started doing experiments on cell colonies and on mosquito swarms, but the systems that we have been studying for a longer time are flock of birds and the swarms of insects. Now, there are two interesting features in these systems, which are the features that basically attracted our interest in the first place. The first feature is the fact that these systems are interacting systems, strongly interacting systems that display collective patterns on the large scale. The second interesting feature is that these systems are out of equilibrium. Indeed, all these examples are nowadays considered as archetypical cases of what is called living active matter, where active is the word that is related to the non-equilibrium character of this dynamical behavior. Of course, active matter does not concern only biological and living systems. It also concerns non-living materials. So in the bottom row, you can see a few examples of experiments that have been performed on granular and non-living active matter, where again, I'm showing you some systems where there are many units interacting, interacting among themselves, and the individual units are out of equilibrium. So let's say that of these two features, I mean, for a long time, we have been interested in particular to the interacting part of the behavior that I've shown you in these examples. The focus that I want to do today is rather on the non-equilibrium feature that I mentioned already. Now, where does this non-equilibrium feature come from? So in this slide, I'm making some very naive sketches, and here I've just shown a set of particles, and usually in equilibrium statistical physics, when we study a system of interacting particles or interacting units in general, what happens is that the units interact among themselves, and possibly they are subject to some noise sources. For example, they are in contact with a thermal bath, and that's it. The overall behavior of the system is uniquely due to the fact that there is noise and there are interactions between the units. In the case of active systems, there is an additional ingredient, which is activity. What does it mean? It means that the interacting units, in this case is the small midges, these insects, they are subject to mutual interactions, they are subject to noise, but they are also endowed with what is called the self-propulsion. Namely, each insect has an internal mechanism, a sort of motor, which allows it to convert energy into motion. Okay, so the system is structurally out of equilibrium, and there is an injection of energy at the individual level. Now, out of equilibrium systems have been studied for a long time in the context of statistical physics, but I mean, in many cases, energy injection occurs at the boundary of the system. So the peculiarity of active materials is that this energy injection is precisely, as I just said, at the individual level. And it has been shown and investigated in many models, and also proven in experiments, that the fact of having activity can dramatically change the collective behavior of the system. And here in this bottom row, I'm showing two paradigmatic examples of this fact. So here on the left, I'm showing you a snapshot of a numerical simulation from the group of Cristina Marchetti. And what you are seeing here is a system of particles which only interact one with the other via repulsive interactions. So in the passive case, this system would not display any non-trivial behavior. However, if the system is active, what one can observe is that there is a phase separation between a disordered background and there are large compact clusters caused precisely by the motility of the units partaking in the system. This is an example of what is called the motility-induced phase separation. Another extraordinary example is the one that has been observed several years ago in the 90s by Thomas Wieczek and co-workers in what is the renowned Wieczek model. So this model, we will talk about it more in details in the following, but at this time, just let me say that it is just basically a system of interacting spins. It's like an XY model, but as compared to the XY model, the particles which have on top of them these directions, these velocities, are allowed to move. So it's a sort of system of mutually aligning individuals that are able to precisely to move in space. So if we consider the passive counterpart of this model, that would be the XY model, and we would not get long-range order. On the contrary, in the case of the active system, the Wieczek model, there is an ordering, a bona fide ordering transition even in 2D. So these are just a couple of examples to show that activity can really dramatically change the behavior of the system. Now, let me go back a little bit to the systems, the biological systems that we have been studying. And what I'd like to do in the first part of my talk is to show you some experimental results that we have been gathering in the last 15 years. Through this result, I would like to show you that actually the role of activity can be different in different systems. So in particular, what I will argue is that the role of activity is not so relevant when we look at the behavior of flocks of birds, while it is crucial when we look at the behavior of swarms of insects. So in this slide, I'm summarizing in just a few words what are the main statistical features that we have been observed in flocks and in swarms. So let me start with the flocks. Here on the left, you can see a nice movie of a flock of birds flying in the sky of Rome. And these systems, clearly you can see it by eye, they exhibit global order. So there is a global direction of motion of the whole group. They all fly together and move together in the same direction. But this is not the only interesting feature that this system display. One can keep looking at other quantities and discover, for example, that flocks of birds display scale-free correlations among the velocities. So this is nice because this is a signature, an indication of the fact that the group is coherent and remains coherent, because individuals are able to influence each other from the point of view of their mutual directions across the whole size of the group. And also, as I will describe a little bit more in details, flocks are able to perform changes of directions and to react very swiftly to external perturbations, as you can see in the movie, when there is a falcon attacking and the flock is able to very quickly change direction and perform a collective turn. Okay, so just to summarize, the flock is very ordered and there are scale-free correlations and a very quick propagation of information. Now let me briefly describe the behavior of swarms. Here on the right, this is a swarm in a park of Rome. Contrary to the case of flocks, here we don't have a global order, so the swarms are not moving groups. They do not move collectively. They remain in the same, localized in the same spot in space. Nevertheless, even if we don't have global order in this case, when we start looking at other quantities rather than the global degree of alignment, the global motion, we discover that also in swarms there are scale-free correlations in the velocity degrees of freedom. So also in this case, there is actually collective behavior because individuals are able to influence each other in terms of mutual directions across the whole group size. Okay. Now, what I would like to show you is that while flocks can basically be described using quasi-equilibrium models, on the contrary, this is not the case for swarms, where, as I mentioned before, one really needs to take into account activity if one wants to model and describe theoretically the statistical properties measured on the data. Okay, so before talking more in details on the experiments that will show you these properties that I have just mentioned, let me introduce with a very concise slide what is the theoretical framework that people use to describe flocking and swarming behavior. So the theoretical framework is the one of aligning models. So here you can see in this box an equation for the degrees of freedom of our individuals, and the degrees of freedoms are the position of each individual and the velocity of each individual. So the equation that is usually adopted to describe motion is an equation where we have an alignment kind of interaction. So the idea, if you think at a swarm, is that each bird to decide where to fly, which is the direction that it has to follow, it looks at the neighbors and it follows the average direction of neighbors. And so this imitation mechanism is encoded in this term here, which is basically alignment. So you see this is a sum over the neighbors. This Nij is what is called the adjacency matrix. It's a matrix that is different from 0 for only for interacting neighbors. So this is an average of the velocities of the flight directions of the neighbors with a certain strength. So it's really like in a ferromagnetic model. And then there is a noise term. On top of that, we need to impose a constraint which is related to self-propulsion. So the constraint in the simplest possible models is a constraint that says that the speed of individuals is fixed and it is equal to a certain value, V naught. Okay, so this is the basic schemes of the VIGSEC model, which has been one of the first models to described flockings, and of many variants that have been developed after the first papers. Now, as you can see, I mean, where does the role of activity come in? So if you look at this Nij, this adjacency matrix, this matrix specifies, as I told you, what are the interacting neighbors. Now, since individuals move, this matrix here, it can change in time. So it is a time-dependent quantity. Because, for example, if you just assume a very simple rule, as in the drawing here in the top row, let's say that individual I is this blue individual, and let's say that it interacts only with the neighbors within this dotted red circle, then what can happen is that at some instant of time, a certain number of individuals is inside this circle, but then since individuals move, at the next time, these two guys can be outside the interaction radius, and some other ones can enter the interaction radius. So this Nij will change in time. Of course, in the static equilibrium case, we would assume that all these particles are fixed. So this Nij would be not dependent on time, and the model would be completely equivalent to an Heisenberg ferromagnetic model. And so this would be simply a dissipative dynamics for an Heisenberg model or an XY model in 2D. Okay? Then there is a generalization of this very simple dynamical equation that I'd like to introduce, because I will need it in the following. So as you see from this equation here, the Wiczek model implies first order dynamics for the directional degrees of freedom. Here we have a first order derivative. But we can actually generalize this model by introducing also inertial terms. And this is the equation that I wrote here in the bottom. So this second equation is a generalization of the Wiczek model, which includes second order derivatives in time. And this is a model that we introduced, and I will explain you why. And we called it the inertial spill model. In the limit, in the overdamp limit, this inertial spill model becomes once again the Wiczek model. Okay, so we have this model has all the possible ingredients that you can think about. It has inertia. It has dissipation, which is related to the first derivative. It has the social alignment force, and it has noise. Now, now that I have defined this very general theoretical framework, I can go back to our natural groups and tell you a little bit where these natural groups lie in terms of the description given by these simplified models of self-propelled particles. They are called in this way. So in this graph here, I'm plotting what is called the polarization, namely the global degree of alignment of a group of self-propelled particles as a function of the control parameter. So the control parameter can be, for example, the strength of the noise. So if you think this model here, you run a simulation, you compute the global degree of alignment, the polarization with varying the relevant parameters, namely the strength of the noise and the strength of alignment. What you get is the following. You get that there is a disorder region where noise dominates over alignment, and you get an order region precisely as in a ferromagnetic model. So from what we understood from all our analysis on the data, flux can be described by this kind of models in the order region. Indeed, in the order region, we have a large polarization, a large degree of global order. We have scale-free correlations because these models are based on alignment, and therefore they are endowed with a rotational symmetry, meaning that in the order region we have soft modes and therefore scale-free correlations. And these are all properties that we have observed qualitatively in flock of birds. On the contrary, for what concerns swarms of insects, as I told you, they are not ordered, they are disordered, therefore they do not belong to this order region. However, I also told you that that swarms display large-scale correlations, so therefore they are in the disorder regions, but they must be close to the ordering transition. They must be in the critical region, precisely because the correlations between velocities are so large. So this is a little bit a very qualitative sketch of how we can describe and interpret what we observe in the data in terms of these simplified models. Okay, so now I would like to comment a little bit more of what we have been observing in the data. And to do so, I would like to show you some results from experiments on flock of birds. And in particular, what we have been looking and what we're looking here are collective turns. So these are flocks that turn collectively. These are real data. And from this data, we can, first of all, we can realize that the turn is not synchronous. So some guys start to turn and the other follow, so that there is a real propagation of the turning phenomenon. And this propagation can be quantified through a propagation law that you see displayed here on the right. So this is the position of the turning front as a function of the time at which individuals turn. And the main feature that I'm interested into, that I want to show you, is that there is a linear regime in all these curves. Each curve corresponds to a different flock, to a different flocking turning event. Therefore, propagation appears to be linear in these systems. And this is why I introduced in my previous slide the second order inertial spin model, because the VICSEC model with dissipative dynamics is not able to explain this behavior. To be able to explain this behavior, you have to introduce the second order derivatives. So to make things simple, here I rewrote the equation of the inertial spin model in the two-dimensional case, where the velocity is specified uniquely by an angle. And in this case, the inertial spin model equation reads like this. You see the first order, the second order derivative, the first order derivative. This is the alignment term. And this is the noise. And this lambda ij is a quantity that is expressed in terms of the adjacency matrix, and is nothing else than a discrete Laplacian. Okay? So now, if we assume that the positions between the individuals are fixed, they do not change in time, we can make a continuum approximation, and we can derive from this equation a prediction for the propagation speed. The propagation speed is precisely the slope of this curve here. Okay? And this is the prediction. So what I'm doing here is I'm doing an equilibrium assumption. Individuals have mutual fixed positions, and I'm deriving with this equilibrium assumption a prediction for the propagation speed. So here on the right, you can see the prediction, which is this blue line, and the real data, the data from the experiments. So you see that this prediction is very much obeyed by the data, meaning that if we assume this equilibrium hypothesis, we get a good description of what happens in reality, okay? And actually, an inspection, a more appropriate and accurate inspection of the individual trajectories shows that this hypothesis is correct. Indeed, it has also been observed several years ago by biologists. When individuals turn in a flock of birds, they perform what are called equal radius turns, and in this way of turning, the individuals keep their mutual position fixed. This means that individuals that were interacting at the beginning of the turn remain interacting during the whole turning process. Another way to check that this quasi-equilibrium hypothesis is really valid, is reasonable, is to compute again from the data the relaxation time on the local scale of interacting neighbors, and this is this blue histogram, and compare it with the time scale of change of the network, of the interaction network, which is the histogram in red. And so what this plot is telling us is that it's true that the network rearranges, but it rearranges very slowly. And all the correlations on the relevant scales of the phenomenon that we want to explain, they decay in faster than the scale on which the network, the interaction network changes significantly. Okay? So this is what happens in flocks. Now let's go to swarms. Okay, so in swarms, I don't want to do. I need to be a little bit quick because I don't have much time. But what we have been doing is that we have been performing experiments to measure space-time correlation functions. So this quantity that you see plotted here, this C of KT, is the correlation function between the velocities of two individuals at a certain distance and at a certain time separation. And then we take the Fourier transform in space. So this is plotted as a function of the wave vector k instead of the distance. Okay? And these curves, they are experimental curves, and each one of them corresponds to a different swarm. Each swarm with a different correlation length psi. Okay, so the decay of each of these correlation functions, as you can see, is different. But what we have been looking at is whether, by any chance, dynamic scaling holds in these systems. So dynamic scaling prescribes that the characteristic decay time of each of these correlation functions should scale as the correlation length. So that if instead of plotting the correlation function as a function of time, we plot it as a function of time divided the characteristic time, which scales with the spatial scale, all the curves should collapse one onto the other. And this is precisely what happens. And from this rescaling, we can get this dynamic critical exponent, which is z equal approximately 1.2. Okay, so what we get is this analysis where from the data we have an estimate of the dynamic critical exponent. Now, if we look at the equilibrium non-active counterpart of this system, the dynamic critical exponent is very different. So the guess that we can take is that we should include activity to explain why this exponent is so low. It is not 2, as one would get in a classical dissipative dynamics for directional degrees of freedom. It is not even 1.5, which is what one would get for an inertial second order kind of dynamics. It is even lower. So clearly we need to take into account activity because equilibrium theories are not able to explain what we observe in the data. And indeed, this is what we tried to do recently, and we have a paper on the archive that we posted a few months ago, where we tried to make a theory taking into account all these ingredients that I have been mentioning, namely the fact that the dynamics can be second order, but also taking into account the fact that there can be activity. And this theory is a field theory, which is basically something that we can write if we don't consider the motion of each individual unit, but we just coarse grain our system and write equations for the coarse grain field. Okay. So and here you can see the result of this field theory, where we start adding ingredients, and in the end, what we can see, this is a sort of a cartoon of the renormalization group phase diagram, but I won't tell you the details. The important point is that we find several fixed points, and one of these fixed points is this red fixed point here, which has a z equal to 1/3. So it's a very low value for the dynamic critical exponent. And if we compare this red value here in the plot, in the right plot, we can see that this fixed point is consistent with the distribution of exponents that we find in the data, which is this black curve here. So the bottom message of this analysis is that only if we take into account activity, we get theoretical predictions that are consistent with what we observe in the data. And another way to directly verify the relevance of activity is, as we did for flux, to compare the time scales associated to the relaxation of the directional degrees of freedom and the time scale associated to the change of the network. And this is what is shown here. So each of these points correspond to, we look at regions of a certain size and we compare the time needed to relax directional degrees of freedom on that size and the time scale needed to change the network on that size. And we see that across all these sizes that we can explore, the two timescales are exactly one on top of the other. I remind you that in flux, these two timescales were very well separated. So here it's the opposite case. Here the timescales coincide one with the other. So clearly we cannot disentangle the dynamics of the directional degrees of freedom from the movement of the particles. And this is why activity is relevant in this case. So this concludes the first part of my talk, and the objective, the task of this part was to motivate the second part, which is more speculative and more theoretical. And the second part basically tries to answer this question: when is activity relevant? And the next question, how we can quantify the degree of non-equilibrium in the system. And on top of that, what changes across the phase diagram? Because I just told you that the situation is different in the Flock case and in the Swarm case. We know that the theoretical framework to describe both of these systems is the same, but they belong to different regions in the phase diagram. So we would like to understand what changes when one goes from one region of the phase diagram to the other. So to try to understand all these points, all these issues, what we did was really a simple exercise that I will describe in following slides. We took a very simple model, the simplest possible model, so Witschek model, okay. And we looked at this Witschek model both in 2D and in 3 dimensions, but here I'm just writing the equations in 2D. So these are the equations that I already wrote in one of my first slides, okay? But we are in 2D, so there is only one variable, this theta I, which is the angle specifying the flight direction of individual I. And being in 2D, we can just write an equation for this angle here. And this term here is the alignment term. And this HXY is just the Hamiltonian of an XY model. This is alignment, the one that read NIJ/VJ in the generic D-dimensional case. And here is the noise, where here I put the noise strength in evidence. Okay, so this is the model that we want to look at, okay? And what we have been trying to do is to look at the quantities that measure non-equilibrium behavior. And the quantities that we have been looking at are the entropy production rate and the violation of the dynamic fluctuation dissipation relationship between correlation and response. But this second part is very preliminary, and I don't know whether I will have time to talk about this, so we'll focus mainly on the first part. Okay, so what we tried to do was to measure the entropy production rate for this kind of model. So the entropy reduction rate and analysis of the entropy reduction rate have been performed a lot in active systems recently, but in the largest amount of cases, people focused on MIPS systems, the system exhibiting motility-induced phase separation. There are basically no analysis on polar aligning particles. So we decided to look at this problem, because we didn't find in the literature anything already investigated on this case. So what is the entropy production rate? Probably all of you know what it is, but let me define it for clarity. So what we do, we have a system where we have some dynamical equations for our degrees of freedom, which are positions and velocities, or positions and angles. Okay. So let's say that we can have many possible trajectories, because this system is in presence of noise. So there is an ensemble of possible trajectories. And what we can do is that we can look at a certain trajectory from time 0 to time tau, this trajectory here, for example. And we can also consider the time reversed trajectory. So this is the forward trajectory. I perform an inversion, a time inversion, and what I get is the backward time inverted trajectory that I will call the backward trajectory. Now, I can associate to each trajectory of this kind an entropy, which is defined as the logarithm of the ratio of the probabilities of the forward and the backward trajectory. Then once I have defined this trajectory-dependent entropy, I can take its average value. Okay, this bracket here represents an average over the ensemble of all possible trajectories. And then I can take the derivative with respect to time. I can take the rate of this average value, and this is precisely the entropy production rate. Now, this entropy production rate has several interesting properties. It is a measure of irreversibility. Okay, so it is a 0 at equilibrium. In our case, it should therefore be 0 when I have no activity and my Wieczek model reduces to an XY model. Okay. And the other interesting feature is that for equations of this kind, where I have a nice simple Langevin equation, it can be computed. So we computed that, and we got some explicit expression of the entropy production rate, which reads in the following. We have this first expression and this second expression, which coincide in the steady state. So we are interested in the steady state. So these two are two equivalent ways of formulate the entropy production rate. So once we have these expressions here, we can just compute the entropy production rate in a numerical simulation. And this is what we did, and I'll show you the result. Okay, so this is the result. And before commenting this result, of course, I have to specify a little bit more the model, because here you see these expressions that I wrote here, they depend on this Nij, on the interaction matrix. So to compute, both to perform the numerical simulations and to compute this entropy production rate, I need to specify how I choose this interaction matrix. Therefore, I have to tell you, I have to decide what are the neighbors with which each individual unit in my system is interacting with. So we consider two different cases, which are the two relevant cases when discussing natural groups. The first case is the case of metric interactions, which is precisely, if you think back at the example that I made in one of my first slides, is precisely the original definition of the interacting matrix in the Wieczek paper of 95. That is, each individual interacts with the neighbors that are within a certain metric range. So these are the metric interactions. But then we can also have a different kind of interaction, which is what we call the topological interactions. And in this case, each individual interacts with a given number of neighbors independently on their distance. And why I'm telling you that these are the two relevant cases for biological groups, because by looking at the data, we proved that for flock of birds, interactions are topological, so are of this kind, while for swarms of insects, they are of the metric kind. So we wanted to look are both situations that can be of interest for experimental reasons. So this is why we consider these two classes of models here. Now, what you can see is that even though the precise shape of the entropy production rate depends on the details of the interaction, whether it is metric or topological, there are some qualitative features which are the same in the two cases. And the one that I want to focus on now is the fact that this entropy production rate peaks in the critical region. Okay, so these light gray lines correspond to the polarization that we get as a function of the noise strength. Okay, so this is basically what helps us to quantify the phase diagram of these models. So here on the right is the disorder region. Here on the left is the order region. Okay, and here where is the peak of these curves corresponds to the critical region. Okay, so in both cases, the entropy production rate peaks around the transition point. Okay, and so this already gives us an interesting description or explanation, if you want, of what we observe in the data, because as I told you, in the data we observe that in swarms, which are quasi-critical, activity is relevant, and we cannot disregard the out of equilibrium character of the system. So swarms would be here. Okay, so swarm would be in the critical region in this diagram. On the contrary, flocks are in the deeply ordered regions, so they would be here, but if interactions were metric, here since interactions are topological. And in this order region, the entropy production rate is very low. This is a logarithmic scale, so here means that the entropy production is really very low. So we understand from this theoretical analysis that what we observed in the data is consistent with this theoretical framework of alignment due flocking behavior. And if we look at how the individuals move in space, okay, and how quickly the interaction network rearranges in space, we find the results that are consistent with this entropy production rate behavior. So here in these three plots, what you can see are the trajectories of individuals in the disorder region here, in the critical region here, and in the order region here. So you can see that in these two extreme regions, the mutual rearrangement of individuals is very low for different reasons, but it is nevertheless very low. While on the contrary, close to the critical point, mutual diffusion is maximal, and we have a stronger rearrangement of the network. So this is clearly a qualitative pictorial view of what I'm saying, but what one can do and what we did was to compute the correlation function of the network and to measure the parameters that determine the decay of this correlation network and plot them as a function of D, and we find quantitatively that the rearrangement of the network is maximal around the critical temperature. So everything is consistent with this idea that close to criticality, the entropy reduction rate is large. So and this is very interesting in relation to what observed in the data. Another interesting property that you can observe from these plots is that the entropy production rate scale as n, where n is the number of individuals in the group. Okay. In the topological case, this is evident because all these different colors are different sizes, and they all collapse one on top of the other once we plot the entropy reduction rate per particle. But this is also what occurs in the case of metric interactions. The finite size effects are stronger, but when we reach large enough sizes, also in this case, we have a collapse of the curves. So the entropy production rate is local, and which is another way of saying that this entropy reduction rate per particle remains finite in the thermodynamic limit. And this is interesting because this is completely different from what occurs in MIPS systems, where you don't observe this scaling. Okay, and maybe if I have time, I will come back to this point. But what I would like to do in the last part of my talk is to address another topic which is related to these results here, and which is the following. Let me consider back again the expression that we got for the entropy production rate, which is this one. Okay. We can conveniently rewrite this expression here in the following way. Now let me tell you a little bit what are these quantities. This G of R is the 2-point per distribution, the 2-point particle, the 2-point distribution of particles. Namely, this is the fraction of particles that are found at distance big R, one with respect to the other, when this big R is the interaction range. Okay. And here within this integral, this function here, epsilon, is simply this quantity here, is a sort of entropy production, density of entropy production rate. If you want, you can call it like that, but it's just this function here. And this quantity Q alpha phi represent the fraction of particles at mutual distance R, which have angles alpha and phi. Now I have to tell you what are these alpha and phi. So let's say that we consider a pair of particles. In this picture here, you can see I and J. These are two particles. Phi is an angle that quantifies the mutual alignment between the velocities of I and J. Okay. On the contrary, alpha is an angle that specifies how the average velocity between the two relates with the distance vector, okay, between I and J. So you can read the definition of this angle from this figure, okay. So it's just basically a way to classify how pairs of particles are distributed in terms of these mutual direction angles and positional angles. Okay. This quantity here, this epsilon alpha phi, is plotted here in the plane phi and alpha. Okay. So you can see that this epsilon is non-symmetric. It has these non-symmetric features. Okay, it is very large here, and it is very low here, and vice versa in the angles. Okay. Now, since we want our entropy production rate to be positive, okay, by construction, it's a mathematical deduction, given that epsilon has this behavior here, we need the Q alpha phi to be asymmetric. So basically, what does it mean? It means that the fact that our system is out of equilibrium, that there is irreversibility, is translated into an asymmetry of a pair distribution that in principle we can compute on the steady state of our system, so we can compute in the data. Okay, so and this is something very interesting, because we started with a definition of entropy reduction rate that was given in terms of trajectories, and we did all our computation, but it's very difficult to compute the entropy production rate starting by trajectories. In a real experiment, you will need the statistics that is not attainable, at least in the experiments that we do. However, in this final expression here, the entropy production rate is given in terms of a quantity that we can compute on the data, and that we can hope maybe with a much lower statistics to be able to compute decently and robustly from the data. Okay. So before talking a little bit more about this Q alpha phi, let me discuss a little bit more what does it mean and where it comes from. So here I plotted again a pair of particles, alpha and j. Okay, so now let me take this pair of particles and let me look at the time reversed configurations, which means that the positions remains the same, but I have to flip the velocities. Okay, so let me flip the velocities. This goes down and this goes down, and I rotate them so I can compare them in an easier way. And so I get this other configuration here. So this is configuration 1, this is configuration 2. So this is the plot of epsilon alpha phi that I've shown you before, this one. So in this diagram here, configuration 1 is here and configuration 2 is here. Okay? And they are related by this time inverse operation. Okay? So the fact that my entropy production rate must be bigger than 0 means that since this is the combination with which the two quantities occur in the integral, the number, the frequency of configurations of kind 1 should be bigger than the frequency of configurations of kind 2 in the steady state. Okay? And this is related to a physical fact, because configuration 1, as you can see here in this case, we are looking at aligned, almost aligned particles in the example that I'm giving you. And this first configuration displays diverging particles, while on the contrary, this displays converging particles. So the fact that these are diverging particles means that in the past, these two particles were at shorter distances than the interaction range, so they were interacting. On the contrary, these two particles, in the past, they were not interacting. Okay? So saying that configuration 1, there are more configurations of this kind than on this kind, means that when you look at a very aligned particles, it's more likely that they have divergent velocities, because particles that have interacted in the past, they tend to align with each other, so they tend to be more aligned. Okay, so this asymmetry is precisely due to the fact that mutual position correlate with the mutual interaction and mutual alignment, which is a typical feature of this kind of systems. But now let me go back. So the conclusion of this first slide is that I should observe an asymmetry in the pair distribution Q alpha phi. And indeed, if I look at my data in the simulation, what I find is that I observe this asymmetry. So this is the same simulation, and here I'm plotting the Q alpha phi, and I see clearly that it is asymmetric. And the white lines are the contour lines of the epsilon function. So the asymmetry is precisely the one that I should have to get a positive entropy production rate. So our numerical analysis gives us consistent results, but the point that I want to underline is that the conclusion of this analysis is that there are quantities that we can observe in the data that represent the signatures of irreversibility, and in particular the asymmetry in this pair correlation function, this pair distribution function is a consequence of irreversibility in our system. And indeed, if I didn't plot here all the plots, but if we look at these plots at different values of D, we see that this asymmetry is stronger in the critical region, and it becomes less and less strong as we go towards the equilibrium limits at small noise and large noise, consistently with what I've shown you before. Now, the other interesting comment that I want to do is, okay, let's say this is, as I told you, this is a quantity that in principle can be investigated in experimental data, but nevertheless, one can ask, this is still a quantity that depends on two variables, alpha and phi. and it is computed for pair particles at mutual distance equal to r, the interaction distance. So what one can ask is whether this degree of asymmetry is also present at distances which are different from the interaction distance. And this is what is displayed here on the right. Here what we do, we take the absolute value of this quantity here, we integrate over phi and alpha, and we get a quantity that only depends on the mutual distance, small r, and we plot it as a function of r. So what we can see is that as the distance between the pairs that we consider increases, this degree of asymmetry decreases, and it peaks at the value of r, which coincides with the interaction range. So this is another interesting feature. We should investigate it more. But if this behavior is robust, if we realize that even when we change the kind of interaction and the particular function of how interactions decay with distance, this behavior remains the same. This is also some quantity that can be looked into the data to get information on the interactions, to make some sort of inference of the interaction range. Okay, so my time is basically finished. So let me state the conclusions. Activity determines the non-equilibrium behavior in polar systems, and in biological groups, I've shown you that it has a different relevance according to whether we look at swarms, disordered system, or flocks or system. And our analysis in these simplified models is consistent with this observation, because what we saw in the model is that the entropy reduction rate, the degree of non-equilibrium behavior, is maximal in the critical region. And the other important message that I wanted to give you is that there are signatures of the entropy reduction rate and on the presence of irreversibility, which are visible in simple quantities that can be measured in the data. And so this is something that, in my opinion, opens also interesting possibilities for experiments and in the future, basically. And this is what we would like also to pursue in a next generation of experiments that we are planning in this moment. So now let me thank all my collaborators and Andrea, with whom we coordinated the group, and Federica Ferretti, who is the PhD student that basically did all this work on the entropy reduction rate. These are other two students who worked on the part that I did not have time to discuss, on the fluctuation dissipation relationships between correlation and response. And thank you very much. Now, if you have any question, please ask.
Thank you. Thank you, Irene, for a very nice talk. Questions? Are there questions from anybody? But, well, I have a very naive question for you, if you hear me.
Yeah.
So what you showed us essentially relies upon a quite clear and simple model that is a sort of extension, if you want, of the previous models that have been studying. So your belief is that this model is sufficiently general to catch the information about, so universal, I would say, to catch information about different situations in different kinds of flocks or swarms or other groups of biosystems that have a collective behavior.
yes, if you consider not the last model that I've discussed, because the analysis of the entropy reduction rate is we did it really in the simplest case, where we have these first order dynamics for the velocities. This model has not inertia. So when I discussed the biological cases, both swarms and flocks, we realized that we need to take into account the presence of second order derivatives. Basically, the presence of second order derivatives means that when you do a field theory, you need to have both dissipative and reversible terms in the dynamics of the fields. Okay, and you need these two ingredients. So you need this reversible part in the dynamics to get results consistent with the data. So yes, the idea that we have is that once you put these ingredients, you get a model which is general enough to describe what we observe in swarms and flocks. Whether this
you mean apart tuning some parameters, essentially you are always in the same universality class in some sense.
Basically, yes. Yes, we are
which makes sense actually, but I don't know, that would be tested obviously in different experiments. I think that when you were mentioning at the end of your talk, and well, it's a very interesting point of view, which is open, disclose new perspectives. I think it's very, very interesting. Thank you very much. Other questions? I don't see any hands up.
Parameter kind of measure of self-organization, close to equilibrium and far to equilibrium, to see whether there's some max entropy production mechanism or minimum entropy production mechanism going on in terms of the degree of self-organization of the systems.
I don't know. What just give me an example. What kind of observable you would consider? I don't know.
No, any measure of self-organization in your systems. So because there's a lot of debate whether self-organization out of equilibrium is actually obeying a maximum entropy production mechanism or minimum entropy production mechanism. It seems that close to equilibrium is rather minimum entropy production, whether it's the opposite, far from equilibrium, but it's far from being established. So I was wondering, you have a very nice tool to measure the entropy production.
One should think about what is the appropriate quantity to look at, because I don't know, maybe here, well, I mean, as a measure of self-organization, I mean, I just think at the correlation length in this case. I don't know what other kind of observables to look at. This is basically a system where the fact that it behaves collectively is encoded completely exhaustively by the fact that you have a correlation length that is big in certain regions of the phase diagram. Otherwise, I think one should think a little bit more quantitatively of what is the quantity that can make the job that you want. In this case, I don't know.
Okay.
There is another question from Giuseppe. Please.
Hi, Irene. Sorry, I'm hijacking Giuseppe's things. I'm Francesco. Sorry, no, I also missed the beginning since I was giving exam, but I was wondering, did you manage to link this entropy production directly to the exchange of neighbors in the flock?
Yes.
Or it can be quantified precisely?
In the formula, if you remember the formula that I've shown you, the entropy production rate is directly proportional to the derivative of the Nij with respect to time.
Okay.
So that there is in the expression there is a direct link between the two. So.
Okay. Thank you very much.
Ciao, Francesco. I see that you got another name. Okay.
So yeah. No. So I guess exactly my
Ah,
experience.
Giuseppe is there. I see.
Yeah, he's there.
You are sharing the same
I arrived
video.
after exams and I
Ciao.
jumped in.
Okay. Other questions? I don't see any other one. So thank you again, Irene. Thank you very much. It's really very nice talk.
Question, I think. I see a yellow hand.
Ah, yes, there is another one. Michelangelo Volpiu raised his hand. Am I correct?
Good morning. Could you spend some words about the response theory on these topics?
Yes, this is something that we have just started. So we just started to look in a very similar class of models. We just started to perform a very simple response experiments. Namely, you have a VHSEC-like model and you add a field and you measure the response, you measure the correlation, and then you just check whether the standard equilibrium relation between correlation and response is violated and how strongly it is violated. And our preliminary results suggest that there is a very similar behavior to the entropy production rate. So you can see from the numerical data violation, and this violation peaks at the transition point. So it is this quantity, which is another way to measure the departure from equilibrium, gives the same kind of information, namely that close to the transition, the system is more out of equilibrium. Yeah, but this has to be, I mean, these are preliminary results, so we really need to make more statistics and to investigate the problem more. But I think this fact that the behavior is the same, that you get the same qualitative peak around the critical region is already very clear.
Okay, thank you.
It's nice that we have many questions. Is there anybody else, or can we leave? I think that we are.
In questo momento
I don't see anybody else. Okay.
Okay.
So
thank you then.
bye Irene, and bye to everybody.
Ciao,
See you next time.
Goodbye.
Hopefully in Parma.